we got rolling here today. Monica and I are still working with research computing to try and get everything set up for the second lab. So there is a handout up here if anybody was feeling industrious over the break and you wanted to get going on this lab. There is a handout here, but it's not the handout we want to give to you. So enjoy your break. All right, don't pre-start this. If we get it done prior to the break, it'll be miraculous, and we'll post it, and then you can go ahead and use it. But my guess is research computing is not going to respond fast enough to have it ready before the break. But it'll definitely be ready as soon as we get back from break. And we'll have the new handout out here with all the instructions on it.
Will the third one be changing? If we were really industrious?
Really industrious, the third one will not be changing. We might just modify the handout a bit just to make it clear, but fundamentally the work that'll go on will be the same. All right. Monica's going to come in at the end of the class today and tell everybody how to go ahead and get a research computing account, so you have access to the computing clusters that they run here on campus. So we did get that part all set up, and we ran a test case, and it seemed to have worked. So hopefully that'll let everybody get accounts before the break starts, and then once you get that, we'll be all set. All right. After class last time, I had a question about something I said, and it was a question about whether the exoatmospheric solar irradiance at the edge of the atmosphere and the ground-reaching solar irradiance was the same term. Because I said that during class. I said, hey, we have the exoatmospheric solar irradiance. Let me pull up the slide where that was. Well, we can actually look at it right here. In the governing equation that we've been working up, we said that the ground-reaching radiance, the ground-reaching irradiance that's going to be reflected from whatever target we happen to look at is the exoatmospheric irradiance modified for geometry in the normal direction to the target itself, times the transmission from the edge of the atmosphere down to the ground. Okay? And the question was, is that really true? And I said, well, yeah, of course it's true. It's right here in the equation. But to me, it's been true because I've been working this equation for so long that I lost sight that it actually isn't quite true. And the question was a good one. The exoatmospheric irradiance at the edge of the atmosphere and the exoatmospheric irradiance reaching the ground isn't exactly the same because it does follow the inverse square law. So I just put together a quick proof to go through this. And you should have all seen this, something similar to this in radiometry last quarter, where you had a point source and you had a surface on a sphere, right, some distance away from that point source, call that R1. And then you had another surface on another sphere sharing the same origin for the point source. And it's a distance R2 away from that point source. All right? And by definition, we knew that if we had flux leaving this surface, you had a certain number of photons leaving this surface, and you were looking within some solid angle defined by d theta and d phi, right here. The number of photons passing through this surface, dA1, is the same as the number of photons passing through this surface. So the flux is the same at both of those points. So I went through and said that the flux on surface 1 and the flux on surface 2 are identically the same. They're in units of watts. Then, by definition, the irradiance on those two surfaces is the flux per unit area. And you can see that the unit area gets larger. Right? So the irradiance, E1 on the first surface and E2 on the second surface aren't the same because of that area. And we're looking at watts per meter squared there. We can represent those areas by the radius, or the distance away that surface is from the point source, times the product of the two arc lengths. Okay, so we get dA1, dA2, that element of area that the flux is going through. And so if we go ahead and plug that into the previous equation for irradiance, you wind up with these equations right here. And So then the relationship that we wanted to figure out was what was the relationship between E1 and E2, those two irradiance values. Well, the fluxes are the same. I'll solve these for flux and set them equal to one another. The d theta, d phi terms go away. They're constant between the two points in space. So we have E1R1 squared equals E2R2 squared, and our relationship is the irradiance of the second surface, the further surface away, is the irradiance of the first surface times that ratio of the squares of the distances they are from the center. All right, so that should be no news, but this is the part that I lost sight of. All right, but in reality, it turns out that it really doesn't matter, right? Because we're 150 million kilometers away from the sun, and we've got 100 kilometers of atmosphere. All right, so if you go through and you do it, the relationship comes out to be this. All right, so we're talking 1/10,000th of a percent that I was off. All right, if you make that assumption, you're going to have that much error in your final answer. But believe me, our errors are never going to be that far down in decimal places. All right, so this one's going to be negligible. But I just wanted to point out that was absolutely a correct assumption. That was brought up after class. I wanted to make sure that was correct. All right. So we just got done talking about multiple scattering, and everything seemed to get a little bit harder when we had multiple scattering in the way, and our nice linear assumption of atmospheric effects sort of fell apart. All right, but it's the reality, and we have to deal with multiple scattering that exists, and so it's something we do need to deal with, and there's really no closed form solution for dealing with it. It has to be modeled, right? We have to go through and use a model similar to Modtran, which we'll talk about in a little lab with, to actually model the amount of scattering that's going on at that location. We just have too many scattering centers, too many particles, too many different kind of species in our path to be able to do that analytically on paper. But easy enough to go ahead and do it in a piece of code. Okay, so the nonlinearity that we were seeing there, right, comes from, well, let's take a look at where it might come from. Now, like I just mentioned, we have a lot of different species of scattering centers, different aerosols, different particles, different sorts of molecules in the atmosphere, all of which either absorb or scatter the ray of photons that's coming towards us. Now, with that in mind, how do we go ahead and try and represent that empirically? All right, well, if I want to measure my radiance, and I want to look at what the effect of scattering might be on that, well, let's draw a picture of what might be going on. All right, so I think I drew this the other day, but let's just refresh ourselves here. We got some energy coming down from the source. It's reflected from the surface. It's some scattering centers. Some of the energy gets absorbed. Some of it passes through. Other amounts get scattered. Some of that energy will go down and hit the target again and be reflected again. Get more scattering centers. Same sort of phenomenon go on. Some are going to go towards the sensor. Some are going to get reflected back down. And this is going to go on forever. Right? We're going to run out of photons pretty soon, or significant numbers of photons. So the effect will go away after several of these bounces occur, just because of, just of sheer numbers and diminishing energy from any of these particles or any of these photons that are traveling around. But let's try and represent what it might look like. All right, so if we have radiance reaching the surface, and we then go ahead and allow that radiance leaving the surface towards the sensor. It's going to go up towards the sensor. It's going to get attenuated or absorbed, all right? And we're going to have a transmission effect that's going to reduce the amount of energy. Right? Tau 2, remember that was the second leg of the L path of radiance from the source to the sensor. So we'll multiply that by the radiance, and that'll give us the amount of radiance reaching the sensor, assuming nothing else went on. Right? But as we just said, some of that energy is also going to be scattered and redirected back towards the ground. Right? So again, what we might have is the amount of energy that is leaving that surface times tau 2 that's been reflected by the surface a second time. And how many of those photons actually got back to that surface? Well, this term S that we have in here is something we're going to call the spherical scattering albedo. It's an estimate. Right? There's all sorts of particles in the atmosphere. They each have their own scattering phase functions associated with them. Okay? And they're all different shapes. If we wanted to go ahead and try and represent each one of those, like I just mentioned before, it's a very, just a very complex problem because there's so many. We do that in codes, right? But just to give you an idea of what's happening here, let's just assume we have a spherical albedo. Right? So we have some amount of energy going in all directions equally. Okay? Not a very realistic one. Non-selective scatterers like water vapor molecules are very close to this. All right, so we attenuate the amount of energy coming back down onto the surface by the scattering albedo in that direction. All right, so let's say we have a 10% reflector, and let's say only 5% of the energy gets scattered back down to the surface. Right? So now you're talking about your original radiance that's been reflected, so it's 1/10 of its size. Now, maybe only 5% of that energy gets scattered back down, so now you're 5% of a tenth, so you're 5/100ths of a radiance unit if you started with one radiance. So even right here, we're starting to talk about small amounts of energy. But depending on your target, it could be a significant portion of the overall signal. Right? If the target's a very dark target, for instance. All right, so that's going to happen again. Right? So what we could do is we could take this combination of terms here, the reflectance of the surface and the spherical albedo term, and square them, because we're going to go through one more iteration of this scattering and reflection. And then we'll go through another one, another scattering and reflection, so we have a cube term, and another one. And obviously these are going to get very small. All right, so if we just, if we go ahead and look what we have here, we have a geometric progression. We can rewrite that, recognizing that we have this scattering reflection term to the 0 power, to the first power, second power, third power, and so on. So we can rewrite that as 1/1 minus r times that spherical scattering albedo. And then place the rest of the terms that represent the radiance leaving the surface up into the numerator. So the radiance leaving the surface, again, was the exoatmospheric solar radiance times tau 1 down to the ground, corrected for geometry, convert that to radiance by divided by pi, and add in the downward radiance term, the sky radiance from that surface. Right. That's all going to be reflected from that surface. We're going to modify it by this term for multiple scattering, assuming we have a spherical albedo, and we only have one scattering phase function. It's only as true if we have just a single scattering phase function that we can use everywhere. And then add in the path radiance or the outbound radiance term on top of that. Yeah.
So 2 questions.
Yeah.
In the second power, the tau that you got over there is also tau 2.
This is a tau 2, yes.
Okay. And then the tau 1 path is considered within the S term?
The tau 1 path is in this L surface term. So what I've done here is re-represented this term to be actually what it was. This is the surface reaching radiance, which is the exoatmospheric solar radiance. There's the tau 1.
But for the other bounces, then it kind of gets multiplied several times.
Yeah. Okay. So once you bounce, let's go back to the figure here. Once you bounce here, there is a tau here and a tau here, right? That you're going through. Absolutely. So this is tau 2. This is not tau 1. It's not tau 2. It's some factor. all right? Because it's not the path to the sensor, it's not the path from the edge of the atmosphere, it's some smaller path.
So that
term,
portion is reflected with the S, or it's embedded in the S term?
no, it's omitted.
It's omitted?
Yeah, there's no term here that's representing that tau term. Now, in reality, most of this multiple scattering happens in what's called the boundary layer, the lowest level of the atmosphere, because that's where most of the particulates and water vapor concentrate.
Mm-hmm.
So the paths are small, so the tau term tends to be higher, but it's not one, right? So the fact that it's omitted from here is an omission. So you really should have it in there. But again, it's probably still close to 1, it's probably 0.7, 0.8, but you're already talking 5/100ths of the original radiance.
Right.
So whether or not that term becomes significant is something to think about.
Sorry, on the subject of taus, in your third term up there, should there be subscript?
Yes, tau 2.
Okay.
Yep.
Isn't albedo just another kind of word for reflectance?
Albedo is a term for a lot of things. Albedo is usually what people refer to as the background reflectance or background scattering.
Okay.
Right? Usually when you refer to a target, you say the target reflectance. Usually when you refer to a background, you say background albedo. Or the
So like a
albedo
car
of
in
the
the
sky.
snow or something like that. That'd be the difference between the albedo and the.
What was that?
Like if you had a car in the snow, you talk about like the car's reflectance and the snow's albedo.
Yeah, sort of. All right, so albedo is not a radiometric term. Right? It's a term that people just tend to use not to represent reflectance. So in what you just said, if you have a car and you have snow, the car has reflectance, the snow has reflectance. Right? But the snow and the tree that's coming out of the snow and the leaves that are on top of the snow and all that stuff together forms a source of reflected energy. And all that composite reflected energy is normally what people refer to as albedo. Right? So it's not a reflectance value, and it's not a radiometric term at all. It's just a term that the literature tends to use to represent the ensemble collected, reflected radiance from other objects in the scene except the one you're looking at. It's a very squishy term, so I don't want you to get confused by that. But usually when people, there are people who do say the albedo of the target, and that's when you sit.
I'm pretty sure Montreal has an albedo term too.
It does. Yep. There's a SALB term in Montreal, which is the surface albedo. That is in Montreal. That is the reflectance of the target.
Okay.
All right, just to confuse you.
Okay.
No, that is actually what the Montreal folks call reflectance.
So when we're talking at the spherical scattering albedo, we're talking about the surrounding area?
The surrounding area and the atmosphere, everything together.
Okay.
All the energy that gets scattered.
Within what kind of visibility? Like where do you kind of cut that off? So if you had
what do you
like
mean
your
there?
car right here in the middle of the desk,
Yep.
you could talk about your spherical albedo being like everything within this area, or you could talk about it within a mile. If you just do it by visibility, like how far can things matter?
Well, in the end, it's really a measure of everything that's reaching the surface. So if you have a really thick atmosphere, you don't have a lot of transmission, but you have a lot of scattering, then you need to start to begin to think about how far away do things still contribute to what's reaching that sensor. So in a sense, you have a situation that looks something like this, right? You have your target here, right? And your atmosphere in close vicinity to your target is scattering energy back down onto it. But your atmosphere over here and over here is still scattering energy. But if the transmission between this point and this point is 0, right, because it's so thick, then this contribution never actually makes it there. Right? But then you have to realize that this is a continuum. Right? As you get closer and closer, you get non-zero transmission at some point. So you just really need to kind of integrate out from that point until you get zero contribution or negligible contribution. So that's a really good question, but a really hard one to answer. But it comes into play when, I mean, you're never going to solve this in pen and paper. You're going to model that. So then it becomes a question of runtime, right? You can continue to model all particles to infinity, but at some point you stop, and the point you stop at is when you stop getting any significant contribution. So that's sort of a roundabout answer to your question. I think there's only a roundabout answer to your question. All right. So what we wind up with here now is an equation for radiance reaching the sensor. We have an additive term, right? Before, this tau2 was sort of written over here, could still be written over here, as a slope term. But now, our independent variable is this term over here. We're dividing by this factor in the denominator. But if you look at what this actually is, what makes it up, it's a term that has a lot of nonlinear components to it. And it's a linear equation. You might think of this as a linear equation, right, where you have your independent variable increasing an exponent each time. But if you were to go ahead and plot it, it's not a straight line anymore. It's going to start to have that parabolic shape that we're seeing over here. So a direct interpretation of the slope of this line at any point now can no longer just be transmission. It winds up being transmission over this 1 minus r times s term. That's in the denominator. All right, so where are we? I think we're finally at the point where we've looked at all the terms that make up this equation. Our little favorite term around here comes back in. This is what we usually refer to if you're watching presentations in the lab on Friday mornings. You will hear people all the time refer to the big equation. This is finally the composite of all the terms that we've been talking to at this point. Radiance reaching the sensor, the energy coming down from the sun through the atmosphere, reflected from the target, the energy coming from the target because it's a black body, modified by its emissivity because it's not really a black body. And so radiance leaving the target due to its temperature, modified by its efficiency as an emitter. Right? So here's our gray body term, which are photons coming from the target itself due to its temperature. We have the portion that is Schott, the F factor, times the downwelling radiance due to solar scattered photons and due to self-emitted photons from the atmosphere itself. So we have the irradiance coming down as a sum of those two terms multiplied by F, the fraction which is Schott. That again gets reflected from the target in a diffuse sense here. The reason we have a diffuse reflectance here is because this is coming from all directions. Right, so we're just using one composite term. Then we have our background. All right, 1 minus F, that's the portion of the hemisphere above the target that's not sky, times the solar radiance that's reflected, that's a resulting of the reflectance of the irradiance hitting a background target and the reflectance of that background target. And we have the background targets themselves emitting photons because their temperature is above absolute zero. Right? So they're acting like a black body. All right. Notice the one thing missing here in this equation is an emissivity term. Okay? When we write the equation in this way, and it's sort of I want to call this its simplified form. We lump the background all as one object. So if we have 5 different background objects, they're all going to have different emissivities. What do we say the emissivity is? Might make sense to say the average emissivity here, but just the way that John had written this out in his book, we just left the emissivity term off. That's another one of those points where, is this a big contributor? All right? Do I have to worry about figuring out the emissivity of all the background objects in my scene? That's a lot of work to find all those out. Do I make a significant error if I say they're all black bodies, as opposed to saying they're all 0.9 emissive? Right? It's a small error on a small term, so leaving it off may or may not have a significant effect. If that background target is very, very hot, then it could have a big problem. But if they're all sitting at ambient temperature, it's probably not going to do that big of an error at all. All right, so now we have all the radiance leaving the target, times tau 2 up to the sensor, plus the atmospherically scattered photons in the solar portion of the spectrum that go towards the sensor, and those same photons that are self-emitted by the atmosphere itself. So if you were to sit down now, you're just going to leave the room, and all you had was a piece of paper and a pencil. What I hope you can do at this point is not have to memorize this equation in any way, but just think through, because you'll forget something if you try to memorize it, right? So what you want to do, and I've literally, I don't know if I want to say I never memorized this, but when I sit down now, I can write out this equation. If you just sit there and you think, okay, where are the photons coming from? And you just start writing down those individual terms, right? So that's where I'd like you to be. I'd like you to be at that point where if you could walk out in the hallway right now and there was a whiteboard out there, you could just scribble down the equation. You look really smart. And you really wouldn't have to ever think about, keeping this in your head. Right? You should always be able to derive this. There's no big surprises here. All right. So now that we have that, we need to take a look at some of the nuances, perhaps. All right. Now, if we have a sensor sitting at altitude, and I'm looking down at the ground, right, and the altitude that my sensor is at relative to the scene I'm looking at is fairly small. In other words, I'm in an aircraft rather than a satellite. The field of view that I'm looking over, in this case, let's say this looks like to be about 60 degrees field of view in the drawing up here. That has a significant effect on all the considerations that I just went over in this equation here. All right, namely, tau 2 and these LU terms. Right? If you think about those, the tau 2 from this point to this point, and the tau 2 from this point to this point, within the field of view of my sensor, is going to vary significantly. Right? So, I'm not very good at geometry. This line is cosine 30 longer than this line. Right? So cosine 30 is about, I have no idea. What was it? Root 3 over 2, sure. Say root 3 over 2. I'll believe that. All right, so it's that much longer. So if you have root 3 over 2 longer path, what's going to happen to your transmission? Well, if you think about transmission, that was e to the optical depth times the extinction coefficient. So the optical depth is going to get longer by root 3 over 2, so your transmission is going to grow by that amount. Right, so what that means is if I'm looking at a pixel in the center of the scene, and I want to try and figure out the ground leaving radiance, right, and I have a sensor reaching radiance, well, I have to understand that I have tau 2 there. But if I am looking at a pixel at the edge of my scene, and I want to figure out the ground leaving radiance, and I have sensor reaching radiance, well, I have that much more extinction due to the increased transmission loss. Right? Plus, I have more upwelling radiance because I have more atmosphere between me and my target. So I get more loss due to transmission because of a longer path, and I get more additive photons back in due to the increased scattering that occurs over that path. Right? So my number, if I had a target here and the same target over here, and everything was the same about those two targets, I might actually get the same radiance at the sensor wait, no, I don't want to say that. All right, I might have a target here, and I might have a target here, and I might get the same radiance at the sensor. Right? And I might draw the same conclusion that those two targets are identical on the ground. But in fact, they aren't. Okay? The fact that I get the same radiance here could be because I've lost more radiance reflected from that target, and I gain more radiance because of the increased path length. Right? So I can make a very dramatically wrong call when I do this. So let's say you had a scene that you collected from a sensor, and you wanted to construct a land cover map, right? And you were doing this using classification scheme that we're going to go over a little bit later on in the quarter. Well, those classification schemes rely on the absolute radiance values that you're observing. So I might say something is grass in the center of the scene. I might say something is grass at the edge of the scene, but in fact I might be very wrong. They might look the same. They might have the same digital counts, but the fact that some of those digital counts are scattered photons from the sky or very blue light, and other ones are lost because of the transmission, and everything just happens to come out to be the same at this point, I'm going to make a mistake. Right? So we do need to correct our scene for these kind of fall-off effects. So if you look over this particular range, I guess I can look right here. Well, no, it doesn't. I don't think these two images correspond to one another. All right, so here's view angles down to 60 degrees. All right, so don't look at this as being transmission loss across this path here, because we're going out much further. I think we're only going out about this far in the drawing above. But you can see that the transmission will drop, and your path radiance term will increase as you get towards the edge of the scene. And it's really all driven by that increase in path length due to the cosine of this angle right here for your field of view. All right, so yeah.
I don't totally understand how upload radiance increases if you're going through like a slanted, like a long slanted path. It seems like, yeah, you'll have more radiance coming off of all those particles, but don't they also encounter transmissions, so aren't they?
Absolutely, yeah. So if you do have this path, so let's say between here and here we have 10 photons, right? And let's say the atmosphere is identical, right? So between here and here we have √3/2 times 10 photons. All right. So each of those is going to scatter more energy, or scatter energy. All the particles will say scatter energy the same. Let's say we're spherical, just real simple case here. They all scatter the same. So cumulatively, with no transmission loss, you're going to get more energy that reaches here. With the transmission loss, the ones from here up will about be the same from here up, right? But you're still adding some more times the transmission term, but it's still in addition to to the cumulative case if I started where the cursor is right now. Does that make sense? Right? Because you always have more. They'll get attenuated more for sure, but there's still more.
I have one question regarding the big equation. That one doesn't consider the multiple scattering, right?
Nope.
It's just single scattering.
That's right. That's right. Now, in practice, we have no way of really coming up with multiple scattering effects. Right? We have to use a model. So what do? When we implement the big equation like this, how do we come up with tau2 and LU and LD and all these terms in here? Right? We run Modtran, or we run some atmospheric model. Typically we run Modtran. Those models have multiple scattering built into them, and the multiple scattering effects are reflected in the transmission terms and the upwelling terms and all the other terms in here. So while it's not explicitly in this equation, it's implicitly in the parameters that we're going to model eventually.
Okay.
All right, so if we go back and we look at all the paths that we talked about when we first started this topic, we had our A path photons or B paths. You can go back to slides and figure out what those were again. But what we're trying to do here is sort of line them up. So each term in the equation here corresponds to the term in order up here. So there should be the same. There's not the same over plus signs. 1, 2, 3, no, 4, 5, 6. 1, 2, 3, 4, 5, 6. this one? It's not important. Let's line them up manually here. All right, so L sub F, the radiance due to path F. What was path F? Well, that was the self-emitted photons from the sky. There you go. That's last term. L sub C, right? That was the scattered solar photons in the sky. There's your term. Right? Then you just kind of walk back through here and see where each of those terms come from. I don't think this is as important as it to deserve a slide on its own. I think if you just remember in your head this picture, or can reconstruct this picture in your head, then you can reconstruct this equation. Very simple. All right. So one thing that's missing at this point is the sensor. All right. Everything to this point has been the radiance that's reaching the sensor, and we have to use some sort of a physical detector material, right? A silicon detector, you know, whatever bandpass you happen to be working in. There's a good material for sensing in that bandpass, and each of those materials have a spectral response function associated with them. So you went over spectral response functions in radiometry. All we're going to do here now is take that sensor reaching radiance at the front end of the sensor itself and multiply that by the spectral response function of the sensor. Typically, we'll use this as a normalized spectral response function with a peak response value of 1. So it's whatever its highest response value will be, we'll call that 1. And that's going to add another very strong spectral flavor to the data. Right? Our data is going to have a spectral shape. Right? Where does that spectral shape come from? Well, if we go back to this equation, sunlight has a spectral shape to it, right? It's essentially a black body curve, peaking at wherever a black body curve at 6,000 degrees Kelvin peaks, right around 550 nanometers. Right? The transmission is going to have a spectral nature to it, right? And that's going to depend on the constituents in the atmosphere, right? So tau 1 is going to be spectrally shaped differently at the South Pole or at the desert in the U.S. Southwest or here in Rochester. You're going to have a different shape to that curve. The reflectance of your target is obviously going to change, right? That's what we're going to base most of our remote sensing on is being able to discriminate different targets from one another. And the spectral shape of the target is certainly very, very best function of wavelength. Emissivity, the same thing, right? If we buy in the Kirchhoff's law and assume our target is opaque, then that's just 1 minus the reflectance. The sky radiance, and due to solar scattered photons, the sky radiance due to self-emitted photons, they're going to have a spectral shape to them. These photons will probably be very black body light. Most of the spectral emission from the sky is very black body light. And these will depend on the particles that are in the sky. Whatever it is that they're scattering. Same thing for the background targets. Background targets have a color. They're going to have a spectral signature associated with it. They're going to flavor the illumination that's falling down onto the surface spectrally. And then tau 2, obviously, same as tau 1, only over a shorter path length. And then the scattered terms themselves. So we're going to introduce this coloring everywhere. And there's one more, and that's the sensor response function on top of it. All right, so for instance, let me ask you this: if you have a white target on the ground and you had perfectly white light coming down, and you sensed it with a silicon detector, right, did you look at spectral response functions for silicon in radiometry? Just generally.
Can you just get the long wave wire and the midway wire?
What's that?
Can you just get the midway wire and the long wave wire through?
No, silicon is sensitive from about 0.4 to about 1 micron. Okay, to go to midwave IR and long wave IR, you're talking about an indium and impidide sensor for the midwave, usually, or a mercury cadmium telluride sensor on the long wave. But in the visible portions, like even in your cell phone cameras, you have a silicon. Okay, so, but if you remember what the spectral response shape looked like, do you have a recollection of what these detector materials look like? You know, so if I were to plot a spectral response function for silicon, I would see, you know, a rise like this, and then you know, a tail off like this. And here we're at about 0.4 microns, or 400 nanometers, and we get up to, you know, the peak spectral response, you know, somewhere about, you know, 0.48 or so. And then once we get out to around around 1 micron or so, we start to drop off again. Okay. So look at silicon for a second. Is this an important part of the spectrum? And that's blue, right? There's a lot of blue that goes on in the world. And when you think about remote sensors, if you had piled all the remote sensors in the world in one room, and you kind of pull them apart by discipline, how many of them do you think study water? There's a lot of water in the world, right? So there's a lot of remote sensors that study water. And look at their, what color is water? Well, water is clear, but what color does water look like? Right? It tends to look blue, and if we don't have a good response in the blue, or we ignore this response in the blue, then we're going to make a lot of mistakes. Right? So we have to live with this. That's the way silicon reacts. But if we ignore that term here, and we just assumed it was spectrally flat, we would make a lot of errors. So we've got to make sure we correct this. So when you incorporate the spectral response function, or the final spectral signal that is detected by your sensor, that's usually what's referred to as the effective radiance. Right? It's not the radiance reaching your sensor, but it's the sensed radiance signal after it's gone through all your detection system. Okay? And that effective radiance is what needs corrected, because that's what's recorded. If I record digital counts as a function of wavelength, I'm recording effective radiance because I've gone through the spectral response function of the sensor. If I were to plot a spectral curve, it would have this term in there. Right? So before I say that spectral signature that I recorded with my sensor is proportional to the spectral response or the spectral reflectance of the material on the ground, well, I got to make sure I remove this, right, their spectral response function. I got to make sure I remove the transmission. I got to remove the upwelled radiance. I got to remove all those things before I can get back and come up with that term right there, that reflectance. So when you hear the term effective radiance, that's usually what we're referring to. Okay, now, a lot of times, you'll have just a single detector. Right? You're not going to be able to record this stuff spectrally. You'll just have one detector. You might have a silicon detector on its own, and that's all you're doing. And if we go back to this curve, what's going to happen? Well, it's going to integrate all the energy over that bandpass region. And that's what you're going to record. Okay? So when you hear the term average or effective bandpass value, what that is, it's the actual integral of the right-hand side of this equation, a single value that comes out. All right. Now, when you're looking at this stuff, now all of a sudden all the shapes start to come into play. So over the next couple of slides here, I just want to show you some of the spectral character of the signal that you might have. All right, so emissivity, right, in the mid-wave infrared portion of the spectrum, 3 to 5 microns. This slanted line right here might be the actual emissivity of a target that I'm looking at. Right? Now, if all I have for my sensor is a single digital count value, because I used a detector and I only recorded one value over the full bandpass, let's say I'm using an indium antimonide sensor here, I get one value out, how do I come up, or how do I back out its temperature? Just pop back a slide here. You know, this equation right here is written in terms of thermal, right? So we have an emissivity, we have a black body equation of temperature T, transmission to the sensor, relative response function of the detector itself. Okay? If all I have is a single digital count, though, what I want to come up with is this LT, the radiance leaving the target. And then I can invert the Planck black body equation and come up with temperature. Right? But I have to back out this spectral emissivity. I have to back out this spectral transmission. I have to back out this spectral response of the sensor. If all I have is a single value, well then I'm stuck. Right? I can't use this spectral emissivity curve any longer. I might use an average emissivity, right, across the bandpass. Right? That's just taking the average of the values between these two dotted lines that represent the bandpass extremes. Right? But I lose that spectral nature to it. Now, what if this curve was significantly higher sloped? Right? So I think I could draw on there. What if I had 3 and 5 microns? Right? And here was my emissivity curve. And here's my average emissivity across here. So that's the average emissivity. This is the actual emissivity. All right. That may not produce a lot of errors. But this one, which has the same average, might. All right. So where would that come into play? So what if I had a material and it was sitting at, I'm going to come up with a realistic temperature. Let's say 300 degrees Kelvin. Okay. My black body curve for a 300 degree Kelvin black body in the 3 to 5 micron region is probably going to have a shape that looks something like this. Okay? So if this was my actual shape of a 300 degree Kelvin black body in the 3 to 5 micron region, and I had an average emissivity curve, in other words, a flat emissivity curve, then I'm going to come up with one answer here. But if this was my actual emissivity curve, I can come up with a very different answer, right? Because, you know, essentially you're going to take these values and multiply them together. You're going to take these values and multiply them together. You're going to take these values and multiply them together, wavelength by wavelength, to come up with your term emissivity times LT as a function of wavelength. Okay? But if all I have is the average, and let's say I do have LT as a function of wavelength, right? I will get a very different answer after I integrate those. So you got to be very aware of these shapes when you're trying to back out answers from these equations, right? So if all you have is a single bandpass value, and you produce an answer from it, people produce answers from them all the time, you're going to have to go through and do an error analysis and say, hey, how wrong could I be? You know, if I have a material, or if my range of materials that I might have emissivities that are shaped like this or like this. All right, and it gets worse. Right? If we look in the same bandpass, here's transmission. Right? In the 3 to 5 micron region, right around 3.5 microns here, we've got a really deep carbon dioxide absorption band. So our transmission goes way down. Actually goes a lot deeper than this. I don't know how much of an atmosphere this is true, but there's points where this curve will come down to 0 transmission in the 3 to 5 micron region. If I have a shape, so let me try and transfer that again back to the drawing here. If I have a target whose emissivity looks like this, all right, and so that's emissivity, and I'm in the 3 to 5 micron window, and my atmosphere, my transmission term, if my transmission term looks like this, right? If that's tau, what's going to happen to my identifying part of my signature? Well, it's masked in this transmission path. Right? So I can get a radiance value out of here, and I could take, emissivity times the black body temperature times the transmission to the sensor. I can compute that, and I'll get a single value. If I integrate that out with the sensor, but it's going to be very difficult or very non-telling of an identifying, or it's going to be hard to use it to identify that actual material if my spectral signature and this deep gap in the transmission have to align with one another. So I always, when people ask me what I do, I tell them, well, I work at RIT. And they say, well, what do you do at RIT? Well, I do remote sensing. Oh, what's remote sensing? Well, I look at objects from sensors from some distance away. Oh, what kind of sensor? Well, thermal sensor. And I started to get into a deep conversation with them, and you start to try and explain, the kind of things it might do. You might identify gases, right, in the thermal infrared regions of the spectrum. You might identify different soil types. You might do these kind of things. And then you try to explain some of the problems, to a layperson. And in reality, what I realized that I actually do is I try to understand phenomenology all the time. I try to understand what's happening in the atmosphere, what's happening with my reflectance or my emission from my target, what's happening with my illumination, and when I combine all those things together, I just try to figure out this puzzle of how all these things kind of cascade with one another. And that's what you wind up doing all the time, no matter what band pass you work in. You're trying to deconvolve these signals, or that's probably not a great term to use, but you're trying to decompose these signals into what they originally were. Okay? And the hope is that you can get back to either reflectance or emissivity in most cases, because then you know something about your target. All right, so tau 2 in the 8 to 14 micron region, the long wave infrared, actually is a little more well behaved, which is nice. It does fall off here out near 14 microns. But you have a deep water absorption band here and a deep water absorption band over here. And you notice those transmissions go down to 0. And they go down to 0 because the atmosphere is too opaque in these regions. Black bodies, right? At least I got the curve kind of right. I was running over here. This is my guess is probably around a 300 degree Kelvin black body, peaks around 10 microns, right? In the long wave infrared portion of the spectrum, you can see what its shape might look like over the bandpass. It actually reaches a maximum, but over here in the midwave, you can see that it's still rising. So we definitely have an issue here. If I was to do thermal radiometry, and I wanted to figure out the temperature of an object, which bandpass would you with? Long wave. Why?
You can most easily characterize it there because it's not varying.
It's not varying as much, right? For Earth temperature objects, right? So if you're looking at things that are around 300K, you're going to look like this. It's a lot easier than working with a curve like this. If I were to go back a slide here and look at this transmission curve, what would you love to do in this bandpass? If you could design a sensor any way you want, what would you want to do?
So that you don't have those deep slope parts?
Yeah, I'd want a sensor that went from 4 to 5 microns. Right, so I was working in this a little bit more well-behaved path. Right? And they designed detectors just like that. So you can have a split band. Now that actually brings up a sort of a neat usage of this. If you could split this band, and have a detector that maybe went from 3 to 3.5, another one that went from 4 to 5. If you then go ahead and you look at what this curve looks like, you could sense this portion of the curve, fairly well behaved. This portion of the curve, pretty steep slope, right? But if I have a slight temperature difference, this curve shape's going to change. And if you have a point here and a point here, you have 2 points that you observe. Now all of a sudden, you might get a better idea of what that temperature is. So thinking about splitting these bandpasses up really helps you. It doesn't help you all that much out here. In long wave, and typically in long wave, you see just a single detector across. Okay, so I'm just going to go ahead to the slide here, and this table is in your textbook. So it's kind of, I don't know if that's easy to read or not. Not easy to read for me. But what we're trying to do here is show you the sensitivity of the terms in this equation. All right. Well, actually, you want to take a quick break, and we'll come back and we'll take a look. So it's sort of interesting. I was just glancing through the text the other day, and it got to this table, and I'm like, wow, it's a confusing table. And I'm looking through it, and I'm looking through it. So I was reading through the text a little bit, and I saw the reference. And the reference is to me on a paper in 1993. So apparently I made this table. And when I was looking, I was like, man, this is the worst table I've ever seen. All right, so I'm going to apologize up front, because it is sort of a confusing table, and it's my fault. All right, so what are we trying to do here? Well, we're trying to look at the different paths, the different types of photons. Right? Go back to the illustrations that we had. And here's essentially the parts of the big equation, the governing equation that make up those individual paths. And below are the values that go into coming up with these terms. On the right-hand side over here is the total sensor reaching radiance. Okay? All right, so the little sections that's broken up into here, it's broken up by integrated radiance reaching the sensor in a particular bandpass. All right, so here, this is visible. So this top little section here is visible data. Okay? This is midwave IR data, and this is long wave infrared data. And the separate lines within each of those represent a different emissivity value. Now you might say emissivity and visible portion of the spectrum, that doesn't make any sense. Well, it's just 1 minus the reflectance. Okay. So rather than just changing the term over here, we left it the same. So this is a 20% reflector, this is a 10% reflector, this is a 1.4% reflector. So a very dark object. All right. Now, if you look at the different contributors to the total radiance, you start to get a feel for what's important and what's not. Okay? So if my total radiance reaching the sensor for a 20% reflector in the visible portion of the spectrum is 4.7 times 10 to the third watts per meter squared steradian. Okay? Let's look at the individual contributions to that. So what's our first term here? This is the exoatmospheric solar radiance reflected from the target. So out of 4.7, 2.3 of that is direct reflected photons from the target for a 20% reflector. So that's a pretty significant term, it's half. The emissivity of the target times the radiance due to its temperature is 9 times 10 to the minus 28th power in this region of spectrum. You could probably ignore that term, okay? Background radiance, right? Reflected off background objects. Here you're talking 0.6 out of 4.7. So that's 12%, 13% of your signal. So it's not negligible. It's small, but not negligible. Same term, but in the thermal portion of the spectrum, right? 10 to the minus 31st. Again, not going to worry about that one. Let's see, sky. Oops. No, I'm sorry, that was the sky. These are the backgrounds. Sorry, F is the portion of the sky that's sky. 1 minus F is the portion of the sky, which is background, or not sky. So the background objects are even a bit smaller. So the background objects here are, let's see, that's what, 0.03? Yeah, out of 4.7. So if you didn't get the background height right, you're not talking about a very large error. Okay. Now, that being said, what's not implied here is how bright the backgrounds are. So if you have a very bright background object, that term will go up a bit. All right, the path radiance terms, the self-emitted and the solar scattered. Self-emitted term, 10 to the minus 29th, again, negligible. Here, 1.75 out of 4.7, that's the path radiance. And that's a big term. All right, so path radiance, direct scattered photons. So what is that? That's 2.3 plus 1.7, that's 4 out of 4.7 is those two terms. So this is a really good exercise to go through when you're starting to look at these kind of things. And apparently I thought it was important enough that we wrote a paper going over all these things. So I actually don't remember writing this paper, but that's okay. All right, so now as your reflectivity gets lower, right? So let's go down to a 1.4% reflector. So now a very dark target. Total radiance at the sensor just around 2 compared to 4.7, right? Well, we went from a 20% reflector down to a 1% reflector. It's a dark object compared to a bright object before. All right, now of that 1.9, what's the most important term in here? Well, 1.75 of it, that doesn't change, right? The upload radiance doesn't really change as a function of reflectance of the target. There's a little bit of multiple scattering that would come into play here, but I do remember this much. When I was running this particular set, I was running a code called Lotran, not Modtran, and Lotran did not have multiple scattering, right? So the fact that these terms are all the same, if you were to redo this study with Modtran, they would be slightly different than one another, but they'd be very close. But look at this, 1.75 out of 1.95 is path radiance. And that's 90% of your signal is the path radiance itself. So now you can start to get a feel, when you have a very dark target, 90% of your signal has nothing to do with your target. You're at a real disadvantage right away. So when people try to do water quality studies, it's very hard. You saw that silicon drop off, right? So it's a very dark target. Because of the silicon dropping off, it reflects a lot there, but we have no signal, right? And so everything appears very dark, even though it's not really dark. It's dark due to the fact that we have a bad spectral response function. So our path radiance is also fairly blue heavy, right? A lot of scattering in the atmosphere, that's why the sky looks blue. Okay. So water quality folks are at a big disadvantage from the start, just because they're looking at dark targets to begin with. They have a lot of path radiance. They got a detector which responds poorly in their wavelength region. So you only got 10% of your signal. Let's see, this is 0.16 out of 1.9. It's actually due to the target itself. You're going to have a hard time overcoming noise. That's something we haven't talked about yet, right? Is noise. So these sensitivities are all good, but then start to look at the noise in your sensor, and then you realize that you start to have a harder and harder problem. All right, so let's jump down to the middle here. Let's jump down to the long wave. All right. The most emissive target here is 0.98 emissivity. All right. At the sensor, we got 8 times 10 to the third watts per meter squared steradian in radiance, and 4.8 of that is due to the target's temperature. Oops. Nope, I'm sorry. 6.4 of that is due to target's temperature. So 6.4 out of 8 is due to the target itself, self-emitting. The reflected photons, right, the solar reflected photons are 4 orders of magnitude down. So when we're working in that portion of the spectrum, we can pretty much ignore the solar part. You know, we're down 4 orders of magnitude away. The atmosphere, downwelling onto the target, right? If we look, what do we have? We have about 1.3 times 10 to the minus 5th coming down from the sky. And in the solar portion of the spectrum, we're down 10 to the minus 9, so we're still down 4 orders of magnitude. But here, we're down 2 orders of magnitude. Right? So the downwelling radiance in the thermal portion of the spectrum is not all that important. Why is that? Well, it's 2 orders of magnitude down, first of all, and we're looking at a target that has a reflectance of 1.4%, right? So we're talking about a very small signal that's going to come into play. Right? So there are times where we say, hey, let's ignore the atmosphere, the downwelling radiance, right? That simplifies us in some of our calculations. Now the path radiance, we're talking 1.5 or 1.6 out of 8, right? There's what, 15% or so. So that's again a fairly significant portion. So in the long wave, the upwelling radiance and the target leaving radiance due to temperature are the primary terms that we're going to have to deal with. And actually, turns out to be a pretty easy problem in a lot of cases. All right, now here's the messy one, 3 to 5. Right? This is in between the two. And if we look at the total radiance, we're talking about. Well, let's look at a fairly reflective target in this case. So 0.8 emissivity, 20% reflective. Right? 2.7 times 10 to the minus 4th watts per meter square radius. So notice that we're down an order of magnitude in radians. So we have less photons in this bandpass. All right, now what's important? Well, out of 2.7, 0.9, or 1/3 of it, is due to the target self-emission. Oh, no, I'm sorry. Is due to the reflectance. Right? 1/3 of it's due to reflectance. 1/2 of it, almost, is due to self-emission. Right? So now we're in a portion of the spectrum where the reflected solar photons and the self-emitted photons are both important. And that's going to depend on where you are in that bandpass. If you're closer to 3 microns, the solar is going to dominate. If you're closer to 5 microns, the self-emission is going to dominate. Overall, in the whole detector region, when we integrate across, you can see that they're pretty close, 0.9 to 1.2. They're almost even. All right, now the path radiance in this particular portion of the spectrum for self-emission, 0.4 out of 2.7, right? Not negligible by any means. And the solar scattered photons are down 2 orders of magnitude, just because of the nature of the scattering properties of the materials in this wavelength region. So this is a very, very messy wavelength region to work in, right? Using a 3.5 sensor at night is a great thing, because you ignore all the solar photons. Using it during the daytime is very difficult. Using a long-wave infrared sensor in the daytime, solar photons almost don't matter at all. So you can measure temperature with a long-wave infrared sensor in the daytime with no problem at all. Using a 3 to 5 sensor is very difficult to measure temperature, but at nighttime it's great. Okay? The detector materials in the 3 to 5 micron region are much more amenable to small pixels, right? So you can get much smaller pixels on an INSBE array than you can on a mercury cadmium telluride array. So you can actually make better spatial resolution detectors in the midwave as opposed to the long wave. Okay? But that's the harder place to work. Right? So you get better spatial resolution but harder radiometry. So there's this sort of a trade-off that you have to go through and see which one's more important to you. But a 3 to 5 sensor at night is great. But your signal's down an order of magnitude. So you have some signal noise issues. So nothing really ever aligns properly, right? You have a great signal noise, big pixels. You know, you always have to do these trade-offs when you're designing the system. But this is really important, and it helps you figure out where you might want to look for a particular phenomenon. All right. Just talk about that. That's essentially the contributions to each of those terms and those bandpasses. All right. I'm just going to skip ahead a little bit because this stuff just is repetitive. All right. We're going to get to a point now where we want to start to understand how we think about errors. Okay? And this is going to be important for the lab you're working on right now, for the photogrammetry lab, because this is the partial derivative error analysis that we'd like to go through in that lab. All right, so let's take a look at a simple problem here and an approach that you may or may not have done before. I asked this the other day, and I don't remember how many hands went up. Has anybody ever done a partial derivative error analysis? All right. So let's take a look at this. All right. So if you look at measurement error, right? If you take a ruler and you measure something, or you take a scale and you weigh something, right? You always have an error associated with that particular measurement. And you know, as we said here, the individual measurement error to describe how closely any individual measurement comes to the truth is often taken to be a root sum square error. So if I'm trying to measure some phenomenon M, and I have many things that go into that measurement, P and I, let's say, as long as those measurements are independent from one another, you can take the individual errors, square them, take the square root of them, add them together, and they add a quadrature, and you can come up with an error of your overall measurement. Okay? It implies that there's no correlation between the measurements, and we can deal with correlation, but in this simple case, we're going to assume there's no correlation between any measurements we might be making. All right. So S sub P, labeled here as the precision, right? And S sub I, labeled as the accuracy, right? Difference between precision and accuracy, you've seen that how many times in your academic career, right? Always, whenever you think about a measurement, go back to those definitions in your head and make sure you understand what's coming from, you know, how well can I make this measurement, what's coming from, how repeatable is that measurement that I can make, right? But those two things are typically independent from one another, so you can add those together, just as I described here for two individual measurements. You could add them together for a single measurement. How precise is the measurement? How accurate is that measurement? And you can come up with an overall measurement. Okay? So you can look at this equation in two different ways. All right, now, if we have some measurement y, that's a function of, you know, however many independent variables that you might have on the right-hand side of the equation, and these observations or measurements that we're going to make are independent from one another, in other words, not uncorrelated, okay? What we'd like to do is come up with the error in y due to the individual errors in x's. So I mentioned back in first class, there's a great book, I think I might have a reference to it. No, I don't have it in the list. But there's a book that came out in 1951. The author was Y.A. Beers. I don't know what the Y or the A stand for. But B-E-E-R-S, not to be confused with Beer's Law. Different person. Had a short little textbook on the analysis of errors. And one of the things that came out of that text, is this approach, which is the partial derivative error analysis approach. All right, so if I were to look at my error in y, S sub y, I could go ahead and look at my equation. So remember, my independent variables were x1, x2, up to xn on the right-hand side. And I could look at the partial of y with respect to each of those individual measurements. Okay? And the overall error is going to be the partial evaluated at my particular observation, right? So whatever values I happen to measure for x1, right? The partial evaluated at that point times, so what is that? What, you know, physically, what is the partial derivative of a function evaluated at a certain point?
How much that affects.
How much it affects the function, right? By definition, it's the slope, right? So as you change the value of x1, you might get to a different point on that derivative. So if x1 is big, it might not have as much of an effect as when x1 is small, right? But this will be how much effect it has at that point. Now that slope, or the sensitivity of the independent variable compared with the dependent variable at that point, is then multiplied by the error that you expect in that measurement, right? Just making that measurement. So S sub x1 is the measurement error that we have right here. Okay? Combination of the precision that you can make that measurement to and the accuracy you can make it with. All right, and then you square that and you add it to the partial of the next independent variable times the error in that independent variable, plus the square of the next independent variable times that's partial. And you square all those, add them all up, take the square root. So you add those together in quadrature. and you wind up with your overall measurement error. All right, now, if you have the unfortunate situation where your measurements are correlated, right, you have to add this extra correlation term here, where you're going to sum up over all independent variables, I and j. You're going to look at the correlation between those two variables and multiply that by the product of their individual partials times the product of their measurement error. Okay. What does that mean? It means you've got to go out, you've got to figure out the correlation, you've got to figure out a correlation matrix, essentially, of all the different correlation values that exist between those variables. Now, 9 times out of 10, you're going to look at a problem, you're going to say, they're not correlated. Or deep down in your heart, you know your individual values are correlated with one another, right? We all do it because we don't want to go through this analysis. Think long and hard when you make that decision and convince yourself that if I do make this simplifying assumption that they're not correlated, that I'm not really going to blow my overall error. Be honest with yourself. I always make the simplifying assumption, and then when a grad student who's working with me comes by and says, oh, I got to do an error analysis, and then I grill them and say, are they correlated? Are you sure they're not correlated? Well, show me what they are if they are correlated. And more times than not, it turns out that they are correlated. But yeah, it's just a matter of how lazy you are. So keep this in mind. Usually when we give you a problem, a homework problem, we'll say assume they're uncorrelated, right? And occasionally we'll give you one that says, all right, go through and do one with correlation. All right, so let's go through an example of this. So let's take a simple radiometry problem. Got a lamp, got an aperture, and we're illuminating a sample over here, and at an off-axis position, I'm going to measure the energy reaching my sensor. Okay. So I have a photon flux coming from my source, and I have an irradiance falling on the surface, some distance away, 0.6 of a meter, and then I reflect, or I look at the radiance coming off this surface, so the reflected irradiance, I look at that at my detector, and I also have some stray light that gets in my detector. I mean, if you ever try to put together a system like this, you know, this is like a spectrometer that you might have on a tabletop instrument. Stray light's always a problem, right? So inside the instrument itself, you're gonna have light bouncing around that gets to the detector that's not coming from your sample. Right? So that's the overall situation we're gonna try and model. Right? What's the error in the radiance that I'm gonna measure here at the sensor? Okay. All right. So what's our equation look like? Well, the radiance at the sensor, L, is going to be the irradiance reaching my sample times the diffuse reflectance, assume we have a Lambertian reflector here. And then I'm going to add in my stray radiance, right? All the photons that are coming from everything else besides the reflected photons. All right, so that's my governing equation for my instrument. And if what I want to measure here is, let's say we want to measure reflectance. That makes sense. If we're using a tabletop spectrometer, what we typically do is try to measure the reflectance of an object. All right, so solve for reflectance, and I have my observed radiance minus my stray light, or my stray radiance, times pi over the irradiance onto the surface. All right, so that's my governing equation that I want to look at, and I want to look at the error in the reflectance when they come up. All right, well, I have a couple terms here. I have L, I have LP, I have pi, and I have E. Okay. So my error in reflectance, S sub r, is going to be the partial with respect to, the partial of r with respect to the radiance recorded at the sensor, partial of r with respect to the stray light, or the stray radiance, the partial of r with respect to the irradiance onto the surface, and the partial of r with respect to pi. Right? Well, last term goes away. Assume we have pi to enough decimal places that we don't have an error, so we can cross that one out. And what we're left with is these three terms. What are they? Well, the partial of r with respect to L, right? That's pi over E, the constant term. The partial of r with respect to the stray radiance is negative pi over E, because of the negative sign here. And then the partial of R with respect to the irradiance onto the surface is LP minus L squared. That's down to the denominator. All right, I square those. I multiply each one by the error. That should be a little s, not a big S. And I wind up with my answer. Okay, so let's figure out how to do that. Well, let's put some numbers in. Now, because it's a radiometry problem, right, we got to give you a little throw here. I can't tell you the irradiance onto the surface because that's not typically what a lamp manufacturer gives you. A lamp manufacturer usually gives you an intensity. Okay? So if I have a mistraceable lamp that I put inside of an instrument, right, I'll usually be told that we have a lamp with a radiant intensity. In this case, the lamp we looked at for the example was 39.6 watts per steradian. Right? That means if I operate at a particular voltage, I'll get 39.6 watts per steradian out. And the calibration that they did said I had an error of plus or minus 1.7. All right, so to figure out the irradiance on the surface, I just used inverse square law. Right? And I wind up with, remember we were 0.6 of a meter away, so on the surface we have 110 watts per meter squared. All right, so that's my irradiance on the surface. All right, so we need to come up with the error in irradiance. Now, remember I had intensity, so I have to come up with the error in irradiance. Right? So how do I do that? Well, here's my equation, right? Intensity over distance squared. So I need to look at the partial of irradiance with respect to intensity and multiply that by the error in intensity. I have that. And then I have to take the partial of the irradiance with respect to the distance times the error in the distance. All right, now I don't have an error in distance here, so now you go back and you look at your measurement. Right? You got to measure from the light source over to your target. Right? What do you do that with? You do that with a ruler, or I guess you can use a laser rangefinder or something. But you got to use something now. Sounds like an easy measurement, but you're going to have error, and how close are you going to get? You're going to get within a millimeter, 2 millimeters, some distance. Well, this is actually kind of a tough measurement, right? Because you're actually measuring from the filament inside of a bulb to a surface some distance away. Right? So it's actually a kind of a hard one. If you look at a filament in a bulb, it actually sits there and vibrates too. So where do you come up with? So we need to come up with a reasonable error. Usually you kind of be conservative and say your error is a little bit higher. You don't want to be too conservative because then your error in your final answer might blow up. But you want to make sure you have enough. So I think in this case we assumed 2 millimeter, 2 millimeter error in our distance. Right? So that's probably pretty good. All right, so you put everything together. The error with in radiance is, go back here for a second. One more. We're going to look at this term first, right? The partial of radiance with reflectance with respect to the radiance recorded at the sensor. So what do we have? Well, we had 110 watts per meter squared falling onto the surface. The reflectance on my surface, oops, not reflectance. Where did 1.17 come from? That's my error in irradiance, right? Where did we figure that out? Oh, error in intensity. That was given back here. All right. All right, wait a minute. 1.7 and 0.17.
Says at the top part, 0.17.
Where did it say it? Right here.
Yep.
Yeah.
Oh, that's the error in L. That's the error in the rating spectrum. All right, I got those two confused because they look the same. This is the error in radiance recorded by the instrument, which is the term we're looking at right here, radiance of the sensor. Okay, so we wind up with 0.17 over 110. So So 0.17 was the error in radians, 110 was the irradiance at the surface. All right, and pi up there. So we square that. Then the next term, right here, what do we have? We have pi over e times the error in the straight line. So we have pi over e times the error in the straight line, 0.03. So there was the error that we had, 0.03. So that one was good. All right, now, this last term, what are we looking at? We're looking at the partial of radiance with respect to the irradiance, which is given by this equation here. Okay. So we have the difference between the stray light and the radiance recorded at the sensor. So if you look back a slide, we measured 3.5 watts per meter squared steradian at the sensor. Our stray light was 0.18. There's the difference. Multiplied by pi, divided by e squared, the irradiance reaching the surface squared, and the 4.8. Next slide. What term are we missing here? We had L minus, LP minus L. Oh,
that's what you saw.
the error in the radiance. All right, so our error in irradiance, when we plug everything into this equation, just apparently isn't here, comes out to 4.8. Okay, so 4.8, we plug in the distance we are away, 0.6, times the error in intensity, plus the intensity that we measured from the lamp, 39.6, over 0.6 cubed, times the error in distance, 2 millimeters. All right, plug all those numbers in, we wind up with 4.8. All right, so work out all those terms. First term, second term, third term, right? Add them together, take the square root, get 0.006. But the neat thing to look at is how important is each of them. All right, so here they're written so they're all the same order of magnitude. So it turns out that the last one here, right, the last term, which is the error due to our knowledge of a radiance on the surface, is the most significant. Right. Oh, I'm sorry, second most significant. The most significant is the first one, which is our knowledge of the radiance, or how well we can measure with the sensor. And then the least important one was the middle one, which was our straight line. Okay, so you can kind of get a feel of what's important. So if you write out all the steps here, rather than writing a piece of code where you never see the intermediate steps, write out the individual steps, you get a good idea of which parameters are more important. So if I wanted to make a better measurement, what would I do here? Yeah, I buy a more expensive detector, right? You get a better detector, you can get the error down. That kind of makes sense in this particular program. All right, so then you just go ahead and solve for radiance, and with all the values that you had, you get 0.095, so you got a 9.5% reflector with a 0.6% error.
So where do you put in the 0.06?
What was that? Oh, nowhere. This is your error. This is your measurement.
So you would say 0.095 with a, so that 0.06.
Yeah. Yeah, so right here, the equations are just rewritten here. So you can express that reflectance as 9.5% plus or minus 0.6%.
This is weird because it's both percentages. If you had something where you're talking about like an actual measured quantity, like an error in meters, would you multiply it by the total and tell you what the plus or minus was?
No.
Or would you say plus or minus 6%?
No. Your units will always work out in your error analysis. I mean, because we're working in reflectance here, we're looking at the error in reflectance, all the units go away. So if you do a unit analysis and it's all the units will go away, and we wind up just with a unitless quantity, or reflectance in this case. But if we were looking at the error in radians, we'd still have units left at this point. So it would be whatever your equation came out to be, in whatever units it came out to be, and your error would have identical units there. So our unit in this case happens to be percent.
Okay.
All right. So this is a really, it's a really powerful technique to do error analysis with. And it always seems like the last thing you want to do. Right? You make a measurement and you want to come up with an error and you're like, oh, I got to go through and do all those partials and I got, right? Because your equation's never that simple, right? The more complicated your governing equation gets, imagine a big equation and go ahead and do an error analysis on the big equation. Right? It's a good candidacy exam question, right, when it comes down to it. But you know, at that point, maybe you start to figure out some of your errors with some Monte Carlo simulations, and you can go ahead and write a code which goes ahead and can solve partials for you, and it becomes a lot easier. But you'll always be asked, I mean, every one of us in remote lab, if you're working on a project with us, we're always going to at the end say, okay, what's the error on that? It's always the last section of your dissertation. Monica hasn't got to her error analysis yet, probably.
No.
But you certainly get there.
Right.
And it will be something that we have to do. So you're going to get some good practice on this in the photogrammetry lab that you're going to do. All right, and again, doesn't this kind of scream exam question for next week? Right. All right, so work through this on your photogrammetry lab. Work through the example here and make sure it all makes sense to you. There's a couple more examples in the textbook that you can go through. And if you can find that Theory of Errors book by White Years anywhere in a garage sale, pick it up for 50 cents or whatever it costs. It is a terrific little book. It's just really hard to find. All right. So Monica's going to tell you a little bit about what we need to do to get research computing accounts. So it seemed like it worked. Maria now is affiliated with the project, so it looks like the process works. So what I did on the course webpage is right after where the Montran lab is going to be written up, I put a link here to research computing. Right? So if you click on that, it'll take you to the research computing page. But let me log out. You can go ahead and log in if you want to show folks.
Yeah, actually, what's the else log in so you can actually show us?
Yeah.
Yeah, so I already have an account, so you can use your account now, because the buttons and stuff won't show up in the right spots. But so you just put in your regular RIT username and password, not your CIS account. And it tells you that you have the wrong credentials like every single time.
Okay, that's not just me?
No, it tells you that it's wrong the first time. Just put the same thing in.
All right. I always thought it was my typing.
For some reason, like, I don't know why it does that, but the first time you put your stuff in, it always says it's wrong. And it's pretty slow.
Sweet. It's like a top door.
Yeah, yeah.
Does anybody have any questions? None? Alright, then you just accept, you have to scroll down to the bottom, I think, for it to light up. And accept. So then you have an account because you have an RIT username and password. So if you go to the bar at the bottom and search research computing, if you just search for Carl, and yep, it'll pop up, so you just click on Carl. My picture?
No, what the fact that you just accepted without reading anything.
Yeah. Oh, we never do that.
I used to work in IT, and we all like, hey, did you read it? Did you read it?
I like how they put that you have to scroll to the bottom sometimes in order to like accept like that actually forces you to do it. And then there'll be a box there that just says request Carl for your advisor. You just click that.
All right, so just a clarification. It's not a supercomputer.
Oh, sorry.
So Research Computing is an organization here at RIT. They're part of ITS, who runs the information technology services for all of RIT. And they're a small group, they're 3 people, but they're in charge of giving us access to high performance computing as opposed to supercomputing. So what you're getting access to by applying here is something that we call the Solvay cluster. It's a 128 node cluster of machines. It's about 2.5 years old right now. So each node is a 2.5-year-old computer. So each node individually is not faster than your laptop, right? In fact, your laptop's probably faster. But what we're going to give you here is access to 128 of them at a time. Right? So if you have one node that's twice as fast as any node on Solvay, you're going to run twice as fast on your laptop. But given 128 of them, you're going to run 64 times faster over on that system. So what they concentrate on is what they call high performance computing, which is the usage of lots of pretty mundane standard machines, but all being used at the same time. And what we're going to have you do is run Montran.
Yeah. So you're going to have to do 72 different Montran runs, so instead of doing one right after another, which you could do here pretty easily, and it would take like maybe an hour and a half or so. But just to show you how powerful it is to have that many machines to be able to use, we're going to have you do it on the research computing cluster. So it's essentially running all 72. If you can get 72 of the nodes, if they're free, then it's essentially running all 72 at one time. So instead of running for an hour and a half, or say they take a minute, an hour and 12 minutes, it runs in 1 minute. So real quick, after you get, you'll get an email back that says you've been approved. So after you get an email back that says you've been approved, you can log back in, and then in the search bar, you're just going to search for the class. So the project is named the class. So if you click on this, it'll take you to this page. And once Carl has been accepted as your advisor, there'll be a line right here that says affiliate with this project, and you'll be able to click on it. So you need to just wait for approval. I don't know, does that come from you or from
Yes.
Research Computing?
Yeah, this morning when I came in, I had the request from Maria. I approved it this morning, and that came out this morning.
Yeah, she affiliated with the project. So Carl will get an email saying you requested him. He'll accept you, and then go back and just affiliate with this research entry. It's really important that you do that for like the research computing kind of like records, and so they know what everybody's working on and stuff like that. So don't forget to go back and do that once you've gotten approved.
And once you click there and you associate with the project, you'll have your RIT credentials will get you onto that system. So your RIT username and password. You have a terabyte of disk space over there, and then access to all the research computing machines.
I think that's it for now. I was like, you're not gonna have to figure out how to use all that stuff on your own. We'll give you like some documentation or set up a time to show you like how to do that stuff. This is just so that research computing can start getting it all set up. So don't worry about the second level. But yeah, and
But if you could do this today, or if possible, do it today. I'll get everybody approved. You'll all have accounts, and then I'll force research computing to react a little quicker, because now they're going to have 13 new users that they need to get up and functional. This is a research computing system. That's why it's called research computing. So it's not meant for classroom activities. It's meant for people doing their dissertations or their sponsored research. But they saw this as a great opportunity. I saw it as a great opportunity to show you guys how to use this utility. You can, like Monica said, you can do this project with a single computer.
yeah.
And it's probably going to take you more than 72 minutes to do this way. And you probably could have done it faster, running it serially, maybe.
Yeah, but I mean, I spent hours and hours and hours trying to learn how to use research computing. So
Right. So this will give you a real simple project to work on over there, and then once you move on to your research, at least you'll have something to look back at and be able to model whatever you're going to do out there. So for instance, Monica's got 9,000 Landsat scenes she needs to analyze, and she'll be able to release 9,000 jobs onto this thing, and each of them will run an hour.
oh well, right now it
Yeah.
takes like 8 hours.
Yeah.
But that needs to.
So 9,000 times 8 hours on a single machine would be
Long
longer than
drive,
Monica wants to be
yeah.
here, right? But being able to use a process like this, she'll be able to get done 128 times faster, at least. And we're actually, if the problem scales even bigger than what this system can handle, research computing will work on farming you out to computers all around the country also. So it's good to learn how to use their systems, learn how to talk their language, and then all of a sudden they'll become, very valuable resources for you and start to do your research projects.
Did you mention about the second lab? No?
Don't do it yet.
Yeah.
Yes.
Okay.
And then,
Just checking.
then we had overachievers asking, can they start the third lab?
No, I was
We're not
just
changing
saying,
that one too much.
that was a big if.
Yeah.
Yeah, I don't think that one should, I'll have to look at it.
Yeah, I don't
think that
I don't
one
think
should
that was
change
gonna
that
change.
much. At least not drastically. The second lab is like completely different though, so no.
So will Montreal be put on the research computer
Yes.
that we're?
Yeah, Botron will be there for you. The nice part is the CIS systems are mounted on the research computing systems. So if you log on over there, you can see your home directories here in CIS. Any software they have installed here in CIS, you can run over there. It's all the same architecture. Cool. All right, we'll see you on Tuesday.